So here I have a circuit. So remember, a circuit, you need to have a power source. So this is our power source. Again, I know it looks complicated, but essentially this is just a battery. This is the negative side of the battery. The positive side is red. So let's just connect this here. Sorry, what is happening? Okay, let's just connect this here like that. So you have here the negative side of the battery, positive side of the battery. So again, if you are looking at the electrons should come out from the negative side of the battery, enter the circuit, and then flow inside the positive side, and so on and so forth. Right? By the way, there's a marking here. So positive and negative. So if we turn this on, so you see the bulb turning on. Right? So this one is an experiment that was accidentally discovered by a guy named Hans Christian Oersted. So Hans Christian Oersted. Oersted is the apelido. He's a Dutch. Hans Christian Oersted, and we call this the Oersted's discovery. So here's the thing. Now look at the compass needle. Okay, I want you to look at the compass needle. Now obviously there are no magnets around. So because there are no magnets around, it only feels the magnetic field of the Earth, right? So as usual, it points to the north-south of the Earth, right? Now let's turn on the circuit, and I want you to focus on the compass needle. Obviously, you know that the circuit is turned on when the bulb lights up, but look at what happens to the needle. 1, 2, 3, go. One more time. 1, 2, 3, go. Okay. We can also do it with the wire on top of it. Okay. 1, 2, 3, go. I'm sorry, it's not close enough. Maybe. Okay. It's kind of hard to see because the wire is kind of getting in the way. But let's wait for the compass needle to stop moving. Just about now. And let's turn on the circuit and focus your attention on the compass needle underneath the wire. 1, 2, 3, go. Notice the compass needle moved. And then Hans Christian Oersted was actually not planning on the experiment. He was just simply, having a circuit on his big desk, and he had a compass around. And by that time, they knew already what magnetic fields are, how magnetic fields work. But obviously, they knew that a compass is just a magnet, and being a magnet, it reacts with other magnets, right? And so when he turned on the circuit, he noticed that the compass needle moved, and that perplexed him because when he looked at the table, there was no magnet around, except, of course, for the compass. And more importantly, he noticed only the deflection in the needle when he turned on the circuit. So obviously, there's only one logical explanation, that the movement of the compass must have been caused by the circuit when it's turned on. Now, obviously, how do you move a compass needle? Well, you move a compass needle by this, right? That's a compass needle. You have a magnet. When the compass needle is influenced by the magnetic field of the magnet, it moves, right? And but again, remember, there was no magnet on his desk, so therefore, there's only one explanation. When he turned on the circuit, somehow there must be a magnetic field created, right? Think about it logically. Compasses are only affected by magnetic fields of other magnets, right? They only move when they detect magnetic fields from other magnets. When he turned on the circuit, just like what we did now, the compass needle moved. So therefore, there must be a magnetic field created somewhere in the circuit. And obviously, as you can see from the demonstration, I had to place the compass needle very close to the wire. So therefore, that's the next hint. scientists knew that the magnetic field was created in the wires of the circuit itself. Okay, so let's observe it one more time. This time, I want you to focus on the rotation. I want you to look at how the compass needle would rotate. Does it rotate clockwise or counterclockwise? By the way, this is kind of confusing, but what I mean by that is look at the compass needle. The green end, imagine that as an arrowhead, right? That's a green end, this one. And if it turns that way, obviously that means counterclockwise. If it turns that way, that's clockwise, right? Look at the arrowhead. Don't look at this one, because if you look at this one, obviously if it turns like that, then you will be confused, because this end it's counterclockwise, but this end, well, it's also counterclockwise. But again, so that you're not confused, just focus on the end, this arrowhead here. Does it turn clockwise or counterclockwise? Okay. First case, we place the arrow above the compass needle. We place the arrow above the compass needle. And again, we have to be patient. We have to wait for the compass needle to stop moving before we turn on the circuit. Now it has stopped moving. Again, observe what happens to the end of the needle. Does it move clockwise or counterclockwise? 1, 2, 3, go. Again, 1, 2, 3, go. Notice that it turns counterclockwise. Okay? So just for our notice, if the compass is under the wire, remember the compass is now under the wire is above it. Under it, the needle moved counterclockwise. Now, how about if we place the compass above the wire? Okay, above the wire. And again, we have to wait for the compass needle to stop moving so that our result would be accurate. Okay, so now let's turn on. Again, let's look at the needle. Does it move clockwise or counterclockwise? 1, 2, 3, go. Again, 1, 2, 3, go. Now it moves counterclockwise, clockwise. So if the compass needle is above the wire, it moves clockwise. But if it's under the wire, it's counterclockwise. Okay? So, that is interesting, because remember, the compass needle will align. Remember, if the magnetic field of a magnet is moving that way, if you place a compass needle here, the compass needle will align to the direction of the magnetic field. So the fact that if you place the compass above the wire, it turns to one direction, and under the wire, it turns to another direction, that can only mean that the magnetic field above the wire is different in direction to the magnetic field under the wire. Feel me? So I hope you get the logic, because you look at the compass needle, it moves one differently if you place it above or under. So finally, scientists found out that that is because, well, obviously you can also do another experiment, and that other experiment is kind of this. This is kind of three-dimensional. What you do is you have a piece of wire, and then that wire, obviously you connect that to the battery so that there's electricity. Then what you do is you can place a compass here, a compass here, a compass here, and a compass here. And then when you turn on the circuit, you try to find out what happens. And actually, when they did this, I cannot do this because we only have a 2-volt battery and our wire is thin, and the effect is not so dramatic if we do that, so it cannot be detected. But if we can do this, what happens is the compass needles will actually do this. Okay, and if you look at that, okay, what does that mean, sir? Well, obviously, if you flex your thinking powers, it means that the magnetic field must be circular around the wire. Okay, so that's the breakthrough. The breakthrough is, now we know that whenever there is electricity passing through a wire, okay, think about this. Whenever there's electricity passing through a wire, the wire develops a magnetic field. There is a magnetic field created in the wire such that that magnetic field is always circular around the wire. Circular meaning it moves that way, this way, this way, this way. So think about it. Above the wire, it's moving towards you. See, my finger is moving towards you. And then it turns, and under the wire, it's now pointing towards me. So that's why when you place the compass needle above, it points to a separate direction when you place the compass needle below. Feel me? So that's the reason why that is. So now scientists know that there must be a circular magnetic field in the wire. And obviously, in the wire, that means all throughout the circuit. So if you have a circuit that is this big, if you measure it here, there's a circular magnetic field here. How about here? There's a circular magnetic field here. How about here? There's a circular magnetic field. So the magnetic field is created along the length of the circuit. It's circular around the wire.